So hello everyone, welcome to my YouTube channel. In today's video, we are going to discuss about regularization. We know that the process of regularization is used to avoid the problem of overfitting. It is a technique that is used for doing the fine tuning of the data by adding additional penalty term in the error function. So the additional term controls the excessively fluctuating function that the coefficients don't take extreme values. This technique of keeping a check or reducing the value of error coefficients are called shrinkage methods or weight decay in the case of neural networks. So how this works is the basically the idea to parallelize the complex models, that is adding a complexity term that would give a bigger loss for complex models. To understand it, let's consider a linear regression. Y equal to, this is my coefficient or intercept in this case. So here y represents the relation, the learned relation or the trained, or you can call it a dependent variable, the target one, and this represents the coefficient as we have already discussed in the linear regression. So in order to fit a model that accurately predicts the value, this y value, we require a loss function and the optimized parameter which can be considered as y's or the various weights. So the loss function here generally is used for linear regression, that is called also known as residual sum squares, that is RSS, residual sum of squares. So let's discuss how it works. So here we know that RSS has the linear regression objective without regularization, and the method will learn by the means of this loss function. Based on our training data, it will adjust the weight, that is the coefficients. If our data is noisy, it will face overfitting, and the estimated coefficients will not generalize the unseen data. So in that case, what is the requirement? That is to regularize it. So it regularizes these learned estimates towards zero by penalizing the magnitude of the coefficients. So how this is working with the regularization? Now suppose this is the price size of the house, and this is the problem of overfitting. So here this is the regularized one. Fine, it is the line is passing very closely to the points, but there is no problem of overfitting. So basically we can call this as appropriate fit, as we have discussed in the previous videos. So this is the price size, and we are using the factors. So here we will reduce the b3 b4 close to 0, and we will calculate the price based on that. So we have regularization techniques known as rich or L2 regularization, LASSO or L1 regularization. So these the two techniques, ridge and lasso regression, is used for doing the process of regularization. They differ in the way they assign penalty to the coefficients. So what is to be done in the regularization? Let's quickly review all such points. Regularization is there to avoid overfitting and to get the appropriate fit, and and that works by adding certain penalty. So that in that case we are having certain coefficients. So a regression model that uses N1 L1 regularization is known as lasso regression, and the model that uses L2 is known as ridge regression. So when we talk of ridge regression, that is the RSS is modified by adding the shrinkage quantity. So the coefficients are estimated by minimizing the function, and we use the function lambda, which is a tuning parameter that will do the fine tuning of the model, which decides that how much we want to penalize the flexibility of our model. So here we are adding the penalty term that regularize the coefficients. So we say this is the mean squared error, which is we know is the difference between actual and the predicted one, and square divided by total number of elements, and the loss function is calculated by actual one minus the predicted one, the square root, by adding this function. So what is this over here? This is the penalty coefficient that is added to the mean squared error, and we get the loss function over there. So by using this we are getting the regularized model by adding the penalty, and this is the penalty that we have added, and lambda in this case is the tuning parameter. So basically the ridge regression increase in the flexibility of the model, and is represented by increasing in its coefficients. And if we want to minimize the above function, then the coefficients need to be small. Ridge regression technique prevents the coefficient from rising too high. It will keep them into control. It will not let them rise too high, and the problem of overfitting will be removed by using that. So the intercept is a measure of the mean value of the response when these values are taken. So lambda is equal to 0 when considered is the penalty term and has no effect and the estimates produced by the ridge regression. So when we say lambda is going towards infinity, the impact of the shrinkage penalty grows and the ridge regression coefficient estimates which approach 0. So as it can be seen, selecting a good value of lambda is very much critical, which is also known as L2 norm. And the coefficients that are produced by the standard least square method are scaling equivalent. And if we multiply these with the certain c, that is the coefficient, and it will be, then in that case it will be scaled by 1 oblique c. So we are not scaling any of the predictor in this case, but the multiplication of the predictor coefficients remain the same. This is not the case with ridge regression, and therefore we need to standardize the predictor or bring the predictors to the same scale by performing ridge regression. So next we have lasso regression, that is L1 regularization. So it is another variation in which the above function is minimized. It is clear that this variation differs from the ridge regression only in penalizing the high coefficients. So what is happening in this case? We use the function this way, which is the adding the penalty to regularize the coefficients. So in case of lasso regression, L1 and L2 regression, the ridge regression can be thought of solving an equation where summation of the scales coefficient is less than or equal to s. And when we talk of lasso regression, it is thought to be an equation where the summation of modules of coefficient is less than equal to s. So s is a constant that exists each values of shrinkage factor lambda. These equations are also referred to as constant functions. So we consider there are two parameters of a given problem. Then according to the formula that we have used, ridge regression is expressed by beta 1 square plus beta 2 square less than equal to s. This implies that the ridge regression coefficients have the smallest RSS loss function for the points and lie in the circle of this equation. And when we talk of lasso regression, the equation becomes beta 1 plus beta 2. Now we are taking the absolute value rather than taking the square. In ridge we have taken the square, and in lasso regression we have taken the absolute value of that. So it implies that the lasso coefficients have the smallest RSS functions for all the values. So here we can see a diagrammatical look. This image shows the constant bigger green areas. Here is the lasso one, and in this case this is the ridge regression. And RSS, these lines here simply represents RSS. Points on the ellipse share the values of RSS. So for a very large value of S, the green regions will contain the center of the ellipse, making the coefficient estimate both regression techniques equal to the least square estimates. So ridge regression has a circular constraint with no sharp points, and this intersection will not generally occur on an axis. And so the ridge regression coefficient estimates will be exclusively to the non-zero points. And the lasso constraint has corners at each of the axes, as we can see, and so the ellipse will often intersect the region at the axis, as we can see, touching this point, but in this case it is crossing this point. So the in higher dimensions the parameters may coefficients may are equal to 0. So we have to choose which technique to use. So when we when to use ridge and when to use lasso. So lot of features in the data set, all features have small coefficients, then go with ridge regression. And when we had talk of loss, when we have lasso, when we have small number of features and few features have high coefficients, then we go with the lasso regression. So ridge is used when lot of features with small coefficients, and this is used when